Hello, everyone, and welcome back to Cup of Java's AI Week 5 lesson. Today, we're going to be talking about linear regression. So last week, we talked about classification, and linear regression is kind of the part B to this type of supervised machine learning. So what is regression? As it says here, regression is a type of supervised learning. We're given an input, we want to try to predict a specific output. So unlike classification, this is not giving a yes or no answer or grouping things into categories. This is giving real number predictions. For example, predicting the value of a home based on square footage, or predicting next week's temperature, or predicting crop yields based on what crop it is and how the weather has been and multiple features that you can use. So regression looks for the relationship between the given input and output values to predict an output value. But linear regression is when you guess that the relationship is linear. So for example, for every 100 square foot increase in a house, the price increases by $2,000. That is a linear relationship because the outputs can be measured with a line. On the other hand, if you have for every 100 square foot increase in a house, the price increases exponentially, that is no longer a line graph. So it can no longer be called linear regression. So the equation for describing a line in general algebra is y equals mx plus b. And m and b are the two parameters that we now want to utilize for linear regression. So in machine learning, we rewrite m and b, which used to be the slope and the y-intercept, as the weight 1 and the initial weight, which is weight 0. So your y-intercept now becomes your initial weight, and your slope now becomes your weight 1. So here's a quick example of linear regression. So if you have the formula of the line as 6x minus 12, that means that the y-intercept is at negative 12. I think this should be positive 12 over here. The y-intercept is at positive 12, and for every 1 hour increase, there is a 6 like increase. So what is the predicted number of likes for a post at 8:30 a.m.? So you're going to substitute 8.5 into the formula for x, because we want to see what the likes for the post is at 8:30. So that's similar to 8.5. So you're plugging that into the equation, and you get 39 when you plug it into the equation. So we're predicting that at 8:30, there will be 39 likes. So as you can see here, this red dot is our prediction. And this line is basically fitted best to what these points are around it. So as you can see, this prediction is quite accurate based on kind of the trend of our line. So for linear regression, our ideal case is that we get a line that goes through all points. But of course, in the real world, that's never going to be the case. So we settle for a line that goes through all the points as closely as possible, and that's called the line of best fit. So if we look back here, you see how this line is not exactly going through every single one of these points, but it is measuring kind of the trend of the data. So since the data is sloping upward at kind of this basic slope, this is the line that best fits this data and will give you the best approximation when you want to know the number of likes based on the time of the day. So in order to tell how good our line is, we want to measure the error. And the error is the difference between what we predict and the actual amount. So our predicted label in here would be 39, and the actual amount of likes would be how many ever you got at that specific moment in time, in reality, not our predicted amount. So the error here is, again, the predicted label, which is y hat, minus whatever the actual label was, which is y. And now we're going to rewrite y hat using our line equation. So if you think back to the last slide, our line equation was the first weight times x plus the initial weight. And so we just plug that into the y hat, And again, of course, the minus y stays the same. Now, error can never be negative. So we want to square this equation in order to make sure that all our error is always positive. And then we want to sum up the errors for all the points that we can get an accurate representation of what the error is for the entire function as a whole. So the symbol over here is called the sum of all. So you're going to sum up all of these values. And then the final equation or the final error that you get is called the sum of squared errors. So the sum of errors that have been squared, or the loss function or the cost function in different cases. And this is basically used to figure out how much information you are losing or retaining when running your linear regression. So training a model means you're learning values for the parameters that minimize loss. And by minimize loss, we mean we want the most amount of information to be retained. So we want accurate predictions based on the data that we already have. So this means having good weight. And as you can see here, this is a really good example of how kind of we want our linear regression model to flow and what we can do to make it better prediction. So you start with all of your features. So if you have house price as your output, your input could be square footage and number of bedrooms and number of bathrooms. Those are all your features. And then based on that, you find a model. And then from there, you're going to update your weights and compute your loss based on these weights and go in a circle again. So you keep going until you find where you can get the lowest loss in your data or the lowest error. And from there, then your linear regression model, then you can call it complete. So now that we've defined error, as remember in the last page we did it as the sum of squared errors. We need to figure out how to update our weights. There are certain things called update rules. And this right here is an equation as to how you update your weights. So you're going to take your new weight is now equal to your old weight minus a times the error. So what is a? A is known as the learning rate. And the learning rate is basically the step size at each iteration while moving towards a function that can minimize minimal loss. So this learning rate is usually a number between 0 and 1, and we get to pick our learning rate. So by toying around with this learning rate, you can also change the error. So you can look at this learning rate and maybe 0.8 learning rate gives you the least error. So that's the one that you would use in your linear regression model. So as you can see here, with replacing error, how do you replace error? Well, you just plug in the new equation that we had. So now because we have new weight values, our equation for error also changes. So when changing your weights, you also have to change the error based on those weights. So this process of updating the weights and computing the loss and the error and repeating is called gradient descent. So more often than not, there will be more than one feature. Going back to my house example, you cannot solely predict the price of a house based on just the square footage. You need to take into consideration many other factors or many other features. So here is how you would hypothetically update for models that have more than one feature. It's the same thing as before, except you're just going to have to use your new features, and your x2 always matches up with your weight 2, and your x1 always matches up with your weight 1. One moment, there is technical difficulties right now. So now we're going to quickly go over a demo of what this is going to look like. So I just pulled the data set from sklearn. You're usually going to want to import all of these statements, and I loaded in my data set. This is the data set of diabetes data. And in this specific example, I'm only going to be using one feature. So as you can see here, I'm taking from one feature of the data set. I'm only pulling one column. And then similar to what we did last time with classification, I'm splitting the data into training and testing, and I'm splitting the targets as well into training and testing. So from there, I'm creating a linear regression model, and this is already a function that exists, and I'm training the model using the training data. Now, coefficients here are what's important. So this is called the regression coefficient. This is an important number. And then our mean squared error, which we also learned about in the slideshow, and then the coefficients of determination. So again, here is how you would plot in Python. If you don't remember how to plot, I would highly recommend going back a few videos where we talked about graphing in Python. It's very helpful when talking about machine learning, especially because everything is so visual. So I would either pause the video or finish this video and go back and try and figure out how to plot in Python. I would also recommend you pausing the video and copying all of this down in order to kind of get a sense of what you playing with the different parts of the data. For example, playing with how much of the data is split into testing and training, and how many features you use. So as you can see here, this is the line of best fit for my data. And their mean squared error here is 2,548, which is not very good. But this is the line of best fit. So that is all for today for linear regression. Thank you guys so much for listening in. And I hope that you guys learned a lot about the next step in machine learning. I will see you all next week.